Hi there. So good morning. So briefly, we're going to look at some of the other technologies involved in using the cloud and how the cloud relates to transporting IP-based video, how the cloud relates to configuring workflows, doing software development, and also how the cloud is changing and how the whole nature of broadcast usages and broadcast competitors and who are broadcast companies is sort of changing along with it. First off, I just wanted to show this is a roadmap slide by the Joint Task Force for Network Media Open Interoperability. The very bottom of the roadmap is moving SDI video from coax to IP. That was sort of the opening gambit in this modern world of moving video to IP, and now trying to do things on, in a cloud or in a networked manner. So there's a lot of work still to be done. There's a lot of work in progress. You'll notice that it involves standards not just from SMPTE, but from the EBU, from the Internet Development Group. It's not a one organization standard way of doing things. It's much more complicated, and there's a lot of different organizations involved. As I was saying, moving from a coax to IP-based video using a 2022 or even now 2110, essentially replaced a cable. You replaced an SDI coaxial headache with now a new IP-based headache, and you've laid the groundwork for the true advances in what can be done. Now that video is packetized, it can be delivered with different technologies that can route it as a flow, to use the terminology from NMOS, to different devices that would do different processes in it. All of these services and workflows can be built and orchestrated in both cloud and on-premise components. And one of the great things about the cloud, of course, is it's infinitely scalable. It's kind of infinitely scalable at an infinite cost, but it's still infinitely scalable. And now we can create apps and have apps communicate with each other in a modern manner that, based on some of the work from NMOS, that ensures a level of interoperability, not just between the connector and the connector on the next device, but in the overall orchestration and management of the apps in between. It's a bit of a balancing act when you look at both the cloud and the edge. The cloud obviously has taken off. We saw the presentation from AWS earlier. I think AWS, they could, if they started listing all of their products and services they offer, they could be here for hours. And, and plus with their acquisition of Elemental, Google, Microsoft, they're all now, there's a lot of cloud providers. The problem, again, with scaling things in the cloud is you can scale, and sometimes you can scale to a cost that becomes very prohibitive, especially when you talk about the operations that are done on full bandwidth video. The other thing that the cloud has as another cost of the cloud is it adds latency. Anything that happens in a cloud is not as well suited for a low latency environment like remote production or a sporting event. Now, to make the cloud to make the cloud work better, some stuff has to happen at the edge. There's some need, like it or not, there's some need for infrastructure for either packetizing video, converting video from one format to another, doing compression so the bandwidth requirements to getting onto the cloud are reduced, and also protecting and creating access control, and managing what streams are allowed in and out of a facility. Sort of the firewall needs to happen still in the premise. A lot of times the encoder, a lot of times the packetizer still needs to be deployed in the edge. Now, With the modern approach to dealing with the cloud, and I don't know if any of you have ever actually deployed things to the cloud, there's a lot of modern tooling for deploying stuff to the cloud. There's containerization, there's VMs, there's orchestration products, and now the edge is getting to the point where it can also take advantage of these modern deployment tools. So now you can build a workflow and spin up the cloud components, load the edge applications, and make the network connections all in a common deployment tool. Another advantage that both edge and cloud share is the ability to operate via APIs. And APIs, for those who are not familiar with them, are application programming interfaces, and this is essentially how one process communicates with another process. Whether a Lambda function that we've seen on AWS invokes an API to cause some other operation to happen. One concept that's come about recently, the concept of virtualization, has been around for a while. Virtualization was sort of the first step towards cloud deployment. The more modern approach, one of the issues with virtualization is every VM needs to have an included operating system, and they need to be orchestrated by a hypervisor level. What happens are the deployment packages become large because they're also encapsulating an operating system. The modern approach, and this is called containerization, it's essentially virtualization, but it's sharing a host operating system. This is a much more practical way for deploying products that have multiple components. So there might be a database component, a media indexing component, all of which can be put in containers and packaged up and be able to and deployed in a manner that's keeping the packages small and easier to move around. Some of the modern tooling that makes this happen, and I just kind of picked ones that I'm a little bit familiar with, I've used the most, and Docker is sort of the container thing that has surfaced for creating and bundling all of the application and the associated resources the application needs without the burden of the operating system. Once you build an application and put it in a container, but now you want to deploy that application in the cloud, but there's some other applications that are also containerized that need to be deployed to make a workflow, that's where a product like Kubernetes comes into play. And this is sort of an outgrowth of Google development. And Kubernetes allows you to deploy multiple containers, create individual or mesh networks between those containers, and bundle that all up into a single deployment package. So now if you want to scale a workflow, instead of deploying each of the pieces independently, you let Kubernetes deploy it and scale it automatically for you. Some of the other tools that have shown up, and that I've a little bit of familiarity with, is Grafana. Grafana allows you to create dashboards to see what processes are going on, to see time series analytics. It's actually an open source product, and it's extremely powerful. Typically, we use it in conjunction, or used it in conjunction with MoogSoft, which is an alert management system where it uses an AI to review what's going on in the different either logs or the different analytics coming up on the dashboards and generate appropriate alerts. This has become a lot more important in the IP cloud world, where you don't actually see what's going, you don't see what's going on at different points of a process, and this allows you to add the tooling that I guess you'd used to have with a series of waveform monitors and different pieces of test equipment. This is the test equipment of the cloud and network. Lastly, Splunk is a very common tool for capturing and correlating logs from different processes. anything cloud-related is going to behave weirdly at some point, and without the appropriate tooling to diagnose, repair, heal, these are the nuts and bolts that make it all work. And there's some links in my paper to the different tools, and you can see some examples there. Another thing that's been changing recently is the broadcasters and relationship with carriers. Carriers originally were just happy to provide bandwidth. They were giving you on and off ramps to cloud services. But also carriers and now have IP backbones that are growing in capacity extremely quickly. What was used to be gigabit backbones, and these are the backbones that are either on the continental U.S. or even the transcontinental backbones, are now moving into the terabit range. And this allows us to do other things like moving uncompressed video over a backbone is now something that's potentially you can do if you can afford the bandwidth cost on it. Also, these carriers are now offering media services because they realize that they've got these really fast pipes for moving things around. One of the things that requires the most data to move around happens to be media and video in particular, so why not start offering specific services for that? The same thing is the cloud providers, which are traditionally Amazon, you could get your S3 storage, your EC2 server infrastructure, you could get networking components, and you could deploy them independently. But now with the Lambda, the serverless component, and now also with, now we're seeing the cloud providers are now offering media-specific services. Some of them, like Amazon, are even creating their own content. I think Facebook as well in that regard. But so now we have now services that are being provided by carriers, services provided by cloud providers, and we're getting a lot of convergence in this, and a lot of convergence and a lot of overlap in a traditional, in traditional broadcasting media production space. This is just a bit of an overview of the different data pipes that are going on under the sea. Obviously, the electricity travels at the speed of light, so you want to work in data centers as close geographically as you can. But right now, there is an ability to distribute things, not over a satellite and a transponder, but to actually distribute things using data pipes. Now, the thing about, if you were, the right agreement with the right carrier, you can lease, when a live event comes up, you can now lease the bandwidth to distribute it to your target and not have to have capital overhead or rely on a satellite network, but you can now rely on the scalability and the growth in the international connectivity, and essentially rely on the backbone of the internet. This is just looking at some of the Silicon Valley companies that are starting to realize that this is something they can take advantage of as streaming has grown as the platform for cord cutters and for receiving content via a streaming provider has growing in popularity. These folks are now looking at how they can acquire what used to be television rights to things. Like Amazon picked up the rights to the British rights to the US Open coming up. A big one, they picked up the Premier Soccer League in English Premier League, and they're handling NFL Thursday night. So I think some of the bids for the streaming rights are now starting to be close to the bids for the broadcast rights. AT&T with their NFL Sunday Ticket. Facebook picked up 25 Major League Baseball games and the rights to watch those on their platform. They actually bid for the Indian Premier League soccer. They bid $600 million for just the streaming rights, but they lost out to Star India, who paid $2.6 billion for combination of the streaming and traditional broadcast rights. So it's just it's interesting that the companies that are offering cloud services are now also taking advantage of these services as well. This is in AT&T and their concept of doing remote production and live streaming from events. AT&T already has they have a content delivery network. Maybe they don't have so many cloud solutions themselves, but they certainly can connect to cloud solutions offered by other providers. This is where traditional television broadcast is really, trying to now take advantage of some of the tools that are being developed for the new wave of non-traditional media delivery. This is an example from Euro Cup, a remote production example where cameras in the stadium were encoded, put up over a network, and the red and blue paths indicate redundancy to a remote broadcast production center, and then using some edge and really not so much cloud, but edge and IP links provided by companies like traditional telcos and carriers. A little bit more modern, okay, yeah. So one of the advantages is native IP. There's orchestration and overall management apps that can now work across multiple locations. Network monitoring and deployment tools can be used. And really, a remote production is a tremendous cost, not only a cost savings, but makes things that are typically very difficult to staff up for and pull off a lot easier. Big example of that is when actually I changed that. It really should be the HBS, International Broadcast Center. Not sure why slides didn't update, but okay. Anyway, this was the World Cup going on in Moscow. You'll notice they had 13 or so stadiums, sending all of the data, all of the feeds from the stadiums going into a broadcast center, and then from that broadcast center, different national broadcasters and different broadcasters, Fox Sports, would take that and then create an IP stream back to their home country for international distribution. That's the master control room at the HBS in the background. I learned something in Moscow. When you write something backwards, that's called Cyrillic. But you can see in the background all of the, when a match, this was between matches, there's nobody in there. When a match was going on, that became a lot more crowded. And from that master control room, their feeds went to the different Telemundo or the different local broadcaster, which would then add their own content to it and create a package that could be streamed via IP back to their host country. Another thing that I wanted to bring up, and this is, I don't know if any of you have been dealing with development so much, but the new way of developing software and the way software connects between one thing and another is what we call is via an API. And the most common API implementation is the representative state transfer, or the RESTful API. And it has a couple really good advantages that it really brings to the table. One is, with these kinds of APIs, things are stateless, so they become scalable and are very useful for the cloud. The operations are minimized, so there's basically there's a few others that aren't as commonly used, but you can create a resource with a post, you can get information with a get, you can update it with a put, and then you can delete it. So to do something, you would enter information into a post command, and you'd send it to an API endpoint. The other thing about the RESTful API is it uses, in the past, XML was the inner machine communication language. JSON is sort of, JSON has sort of replaced that. That's a JavaScript native. It's a native non-compiled language, unlike XML, that's both human readable and machine readable. So it doesn't need to be processed in a API. It can be sent directly, plus you can actually look at it. I had a little mention about Swagger and an example, but since we're running this from a computer up there, can show, if anybody's interested, I can show the example later. Swagger is a really nice tool. What Swagger does, and if you've ever worked with manufacturers and they create these really big protocol documents and all this documentation that they spend a lot of time doing it. It's never quite up to date. What Swagger now does is it creates an endpoint that generates the documentation from the code itself because of the machine-readable nature of JSON. And it also creates an endpoint where you can literally go up to a computer and press a button and try out an API. Like I said, there's an example there I can show people independently later. But it's just, it's becoming a much more popular tool for creating. So, the developers develop code, they create this kind of API, it creates a documentation and test endpoint that they can use and that other vendors or other customers or any other, other people can try out and, and verify that it's working correctly before connecting the different programs together. Sort of the unit testability system in the API. Just a little bit of an overview. I'd mentioned earlier APIs. One of the biggest standardization efforts going on is by the Network Media Open Standards, and they have a model for everything that might happen in a broadcast or production chain. Essentially, you have senders, receivers, and then streams would be flows. They group them into devices and nodes, and I just wanted to share that because that's a little bit of the terminology and jargon you encounter when you look at this. Now, the other thing that makes NMOS a bit different than a body like SMPTE is instead of writing standards by committee and publishing them, all of the work by NMOS goes on to GitHub, and GitHub is the ultimate source code or sharing site. It allows, it's the backbone of open source software development, and it's becoming a very popular mechanism for interoperability. So essentially, by contributing and by developing and sharing via GitHub, they can reduce the cycle it takes to develop and publish a standard considerably. There's still complexity in it, of course. Take a look at how NMOS stacks up in a networking environment. They kind of, a little bit of this is glossed over in an abstracted away, but you still have your receiver side layers, whether they're the MAC layer or the IP layer or anyway, the interesting stuff really happens up in the media application layer, which would be the top layer in the OSI model. And this is typically the layer where an encoder, a decoder, one of the advanced SMPTE functions like hit lists or FEC or FEC, that would take, all of the industry-specific stuff happens at the IP layer. So what's happening is a media application is built. It's now relying on all kinds of technology that's developed by the internet and networking bodies to ride on top of, and it becomes sort of this technological pyramid. And this sort of is an example of it, and you have the internet and engineering technology, you have SMPTE, you have Advanced Media Workflow Association, Video Services, EBU. All of these organizations are contributing to the different components to allow us to create IP-based network, IP-based media solutions. And this is the case for both cloud-based as well as edge-based. And you know, there's a whole lot of stuff that's going on outside of the normal SMPTE engineering body, but is just as important and is sort of the backbone and framework for that to take place. And that just brings us to questions, just as this timer counts down to 0 over here.
You have time? You have time for a question if anyone has one? Okay, wait, I have one question then, if you're, just to kind of reemphasize something. You mentioned open source and the APIs, and with everything changing so fast, do you think that there's obviously a greater need than ever before for open source APIs and open APIs and standards around that area? Standardizing the APIs and having them open?
Yes. Again, the complexity involved in it, and I don't know if anybody has worked on actually deploying something and standing up a whole workflow in AWS or in a cloud environment. There's a lot of things that need to work together appropriately, and the amount of, any tool that can automate API integration, any tool that can automate deployment or set up the network connections, those become critically valuable and, in getting it up and running. And then the same kind of tooling for monitoring the health and, and the behavior.
Okay, thank you very much. Thank you.
Thank you for watching. If you enjoyed this video, please tap the like button and also subscribe to our channel to receive notifications when we add new content. For more information about us, please visit SMPTE.org. We'll see you next time.